So now let's talk about cross-validation. Cross-validation is really a key concept in the field of machine learning. And it's a really neat idea. What is it all about? Well, we already talked about splitting up our data in a training part, a part of the data that we use for training, and a part of the data that we use for testing, our test set. And the idea is the model in the training phase only sees the training data, and thus we can use the test data in order to evaluate the performance of the model. And the idea is that this would give us an unbiased, fair evaluation of the model. It would give us performance estimates that should be very close to the performance we see on real-world applications. So the performance would be similar to what we get down here because the model has not seen the test data. So what's the problem with the split? And let's assume we do a 70-30 split, so 70 for training, 30% for testing. So what's the problem? Well, the problem is actually quite obvious. The problem is that you can only use 70% of the data for training and only 30% of the data for testing. So that's the problem. Yeah, you would actually, what you would like to do is use 100% of the data for training and all your data for testing. Yeah, then we would make much better use of your data. But that's not so easy to accomplish. But cross-validation gets you there. It gets you almost there. It's really close. So what you do is you split up your data set in K parts. And here we do 5-fold cross-validation. So we split it up in 5 parts, 5 equal parts of your data. And then you train your model several times. So in the first run, you train your model on these first 4 folds, and then you test on the 5th fold. And then you do another round. And then you use the 4th fold for testing and all the others for training. And you do this 5 times. So you get 5 performance evaluations. Each used 20% of the data. So in total, you have evaluated your model performance on 100% of your data set. And additionally, you could use 80% of the data for training. You see, you can make much better use of your data. And well, the downside is that now you have to train your model 5 times. So it's a little bit more compute intensive. But with modern CPUs, you can parallelize that task quite easily. So that's the basic idea. And you can do 5-fold, but more commonly is to use 10-fold cross-validation, which means you train your model 10 times and you use 90% of the data for training and 10% of the data for testing in each fold. But at the end, you average all your 10 performance evaluations of your 10 folds in order to get a performance evaluation on the whole data set. So this is how you make better use of your data. So in order to make this clear what cross-validation does, I would like to run you through some easy-to-read pseudocode. So cross-validation, what does it do? Well, it basically is a function, a cross-validation function. It takes data and K is the number of folds you would like to create. As I said before, 5 or more often 10 are typical values. So what does this function do? Well, it splits up the data in K equal parts. And then there's a loop that runs over K from 1 to K. And fold index is our loop variable. So now we create 2 temporary data sets. The training data, which is all data except for the fold index part. So let's say we have 10-fold cross-validation. So the training data consists of 90% of the data. The test data contains only the 10% of the data that is indexed by fold index. So training data 90%, test data 10%. Then we train our model on the training data in order to get a machine learning model. Then we evaluate the model we trained here on our training data using the test data. So obviously, it's a fair evaluation as the model has not seen the test data. It only was trained on the training data. So we compute some kind of performance evaluation like AUC or accuracy or mean squared error or something like this. You could also compute several performance metrics if you would like. And then we store this metric in some kind of a data structure in a list. So at the end of the loop, after you done this 10 times, you calculate the average performance over all k folds. You might also calculate the standard deviation to see how much the performance evaluations of the single folds vary, which is also kind of important information. And then you return the average performance. So this is cross-validation. From the main program, it might look like you load a data set, you set a value of k, and then you call your cross-validation function providing the data set in k, and what you receive is a performance estimate. So what cross-validation only does is it gives you a number, like how good does the model you choose here perform on your data set. And this performance evaluation should be as fair as possible. It should not be like too optimistic and should not be too pessimistic. It should be a fair evaluation. You just want to know how good your model that you choose performs on your dataset. So this is the key idea of cross-validation. And performing cross-validation means computing a performance estimate. How good will the model perform on this dataset? So why is this important? Why do we have to make better use of our data? Well, there is a core principle in machine learning. It's called the learning curve. And the learning curve might look like this. And the key idea is that, well, your model will get better the more data you have. If I train my model on only 100 data points, I might get a performance in this range, maybe 70%. But if I have 200 data points, I might get 80% accuracy. Obviously, the more data you have for training, the better the model will be. And this curve usually is steep at the beginning and then flattens out if you have more data and more data. Obviously, if you have already 1 billion data points, then having 10% more doesn't give you better performance. There's this kind of a shape. The problem is that usually you do not know where on the learning curve you are. You can try to find out, but it's often not so easy to really determine where you are on the learning curve. But there is some kind of a learning curve. So what happens now if you do a 50-50 split? Let's assume we have 200 data points and we do a 50-50 split. Then I can train my model on 100 data points and I get performance evaluation like that. So I would need to assume that my model performance will actually be only 70%. But in reality, I have 200 data points, so I can train my model on 200 data points in order for putting it out for production. So I would end up with accuracy of 80%. So as we have to split up the data and can only use part of the data for training and the other for testing, when we test our model, there's always this bias towards worse performance. So the performance evaluation we get here in this procedure has always a negative bias. The model seems a little bit worse than it actually should be. So the advantage of cross-validation, especially tenfold cross-validation, is that you only have to move a little bit to the left now because you can use 90% of your data for training. So you only go a very little amount to the left side, which means that your performance evaluation will be very close to the true performance. So cross-validation is really the gold standard for performance evaluation in machine learning. It's a great tool for assessing the performance of the model, which allows you model selection. You can apply it anywhere. It's very good applicable to almost any situation. It makes very good use of the data. 100% for testing, 90% for training, which is pretty amazing actually. And it gives you a nearly unbiased and robust performance evaluation. Unbiased in the sense that you only go a little bit to the left in the learning curve. While with a 50-50 split, you go a lot to the left, which gives you a very biased performance evaluation. So cross-validation is really a very useful tool, and it should be in your toolbox, and it should be the default way of working with data and evaluating your model. So we talked about using cross-validation to assess the performance of the model, to get a performance estimate. That's one very common use for cross-validation. The other very common use for cross-validation is to do model selection. And model selection has to be done for almost all machine learning algorithms. So usually you have some kind of a complexity parameter. You could think of that as the number of parameters in the model. Yeah, the more parameters you have, the more complex the model will be. And this allows the model to better adapt to the training data set. So you will get a better performance on your training data set. The training error will be better if the model is more complex, because you allow the model, as it has more parameters, to better fit your training data set. So that's the basic idea. If you increase the model complexity, your training error will go down because the model has more flexibility to adapt to the training data. At the end, if you have a very high model complexity here in this range, the model might already learn by heart all your individual training data points. But this is then not really useful because the test data might look quite different. So what happens is that usually there's a sweet spot. There's this range of underfitting where the model complexity is not high enough to capture the key aspects of your data in this range. Then the training error will be high and also the test error will be high. On the other hand, if you have overfitting, then your training error will be low, but you have a high test error because the model does not really identify the key aspects of your training data set. It's more likely to learn by heart all little noise that is in your training data. What you can do now is to vary the model complexity. Set the model complexity to, let's say, this is 1. And then you perform cross-validation, which gives you a performance estimate of both the training error and the test error. And then you do this for model complexity 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And then at the end, you plot this test error curve, and you will identify usually there's some kind of a sweet spot. And this is then the right model complexity for your problem and for the data you have in order to solve your problem. So cross-validation is really very useful. Look, there are so many things we do not know yet about our data set. For instance, what model should we use? Should we use a linear model, a quadratic model, a tree model, or whatever kind of model? So we do not know yet what model fits our data best. So in order to find out, we do cross-validation on our data set using different kinds of models. And a model that gives us higher accuracy obviously fits better to our data set and can model the data in a better way. So we can use cross-validation for essentially model selection. Then we can use cross-validation to fit the model complexity. So we do that by varying the model complexity, like the number of parameters in our model, and then perform cross-validation for each set of model complexity, and then look at the test error and see which set of model complexity parameters might minimize our test error. Then when we want to optimize the cutoff for optimizing sensitivity and specificity, we can also do this using cross-validation. And at the end, we need to know how good our model will perform on unseen data. So this can also be done using cross-validation. So cross-validation is really like our main tool we use to answer questions we have. Yeah, we answer these questions to our data set using cross-validation. And this is why it's such an essential idea. Next, I would like to give you some insights into how to use cross-validation in the right way to avoid common pitfalls that might not be very obvious for you. So many talk about this Kaiserslautern paper, cross-validation pitfalls, and they identified 4 main pitfalls you might encounter. So the first one is reporting a cross-validation error as an estimate of error. So what does this mean? Well, here we have an example of a cross-validation run. This is from the Hasty book, a very good book on statistical learning. And what we see here in blue, these are cross-validation estimates using different kinds of model complexity. They choose here a different number of parameters in the model. And well, you get your mean performance estimate and your standard deviation. So how do these performance estimates of your single folds vary over your 10 folds? And you basically get this typical line that you would expect, even though, yeah, the minimum is not that obvious here. Look, this is actually essentially this plot here, the test error. But you see it flattens out a little bit. So the curve doesn't really steeply go up after the minimum, which is often the case that you do not see this sharp increase here. Nevertheless, this is a typical curve for performing cross-validation to fit the model complexity. So we did this, and the main objective we have is now to identify the minimum, which might be this data point here, 10 parameters. It seems to be the best value. And that's the main purpose of doing this experiment. You vary the model complexity, do cross-validation for each parameter value, and look for the minimum. So the pitfall you should avoid is to go here to the minimum, read off this number, which might be 0.12, and assume that this is the performance of the model that you would see on unseen data. That is not necessarily true, because the performance estimate of 0.12 is kind of optimized by you by identifying the minimum here. So what should be done now is that you should have independent data that you have not used for this cross-validation run. And then take this model with 10 parameters and train it on your whole data set, and then estimate the performance on this data set that you haven't used yet. I know it's a little bit of a technicality, but it's kind of important that you understand that the minimum you have identified here is not necessarily the performance of the model that you would see on unseen data, because you have used this data to fit this parameter here. And therefore, the performance estimation might be a little bit too optimistic. So that's pitfall number 1. Pitfall number 2 gives rise to repeated cross-validation. So the thing is that when you do cross-validation, you obviously randomize your data set into these 10 folds. But as it turns out, there's some variance in there. So what has been done here is a cross-validation run, or essentially 50 times a cross-validation run, 50 times 10-fold cross-validation for each number of model complexity. Number of components is the model complexity. And you see here that this is the average of the performance you would see using these 50 repetitions. And this is the minimum and maximum. So you see that as you randomize the data into your folds, there might be some good randomizations and there might be some bad randomizations. and when you only do one cross-validation run, so if you only do cross-validation once, then you might end up with actually this minimum here, or you end up with this maximum here. So therefore, when you do cross-validation in order to estimate the performance, you should do it several times. And let's say at minimum 20 times, maybe up to 50 times. And then average over these cross-validation runs. This would then give you a much better performance estimate. You essentially cannot trust a single cross-validation run. You should really do this several times. And yeah, you see, it really depends on the number of parameters, but at the end, the variance is quite large. You see how much variance is there. And the variance only comes from the way you randomize your data points into these folds. And you need to check for that. Next, and this also emphasizes the importance of repeated cross-validation. So when you want to fit a hyperparameter, essentially the model complexity, like in this plot here, then you need also do the cross-validation several times. I will now zoom in to this table here from the Kaiserslautern paper. And yeah, it doesn't really matter. We can look at this row here. So they want to fit logistic regression or rich logistic regression. And you need to fit the model complexity, the parameter lambda you have to fit. And they did 50 cross-validation runs. And in 7 of them, the optimal lambda, the lambda that gives you the best performance, was below 0.09. Well, in 8 cases, it was above 0.28. And the most common value was 0.16. So 0.16 was the value that had the best performance the most time. So you see, there's a lot of variance in that. So if you really want to fit these parameters to identify this minimum here, you want to identify where this minimum is on this axis, then it's essentially not enough to do one cross-validation run, because you could end up with this value or with this value or with this value if you don't only do it once. There's too much randomness involved. And therefore, what you have to do is use repeated cross-validation with n equals, let's say, 20 to 50, something in this range. And average all these performance estimates for each of your lambda values. And then use the mean error to select the best parameter. In essence, you cannot trust a single cross-validation run when you want to fit the model complexity parameter. So the next concept to avoid a pitfall is called nested cross-validation. And it comes down to this plot again that we talked about before, that you do cross-validation for your complexity parameter and then identify the minimum here, and then assume that this minimum would give you the fair performance evaluation. And that's not true. So if you do this cross-validation run for fitting your hyperparameter, then the minimum you obtained is not your generalization error. It's not the error you would see on new data. And this is what they've tested here. So they did an experiment and identified that the 10-fold cross-validation error on a data set have a distribution like this one. It seems like to be a Gaussian. And the errors vary between 0.1 to 0.6, something like that. But the true error on the data set is in this range. It's about 0.5. So you see that the error estimates of the cross-validation run is usually too optimistic. Therefore, what you have to do is to do nested cross-validation, where you have an external cross-validation run that's sole purpose is to estimate the prediction error, and an internal cross-validation run that you can use to do model selection, parameter optimization, variable selection, and so on. The basic algorithm looks like this. So you have an outer loop. This is your outer cross-validation run, where you split your data set into a few folds. And for each fold, you perform an inner cross-validation run. And within this inner cross-validation run, that only has like 90% of the data that you're currently using, you can do whatever you want. Yeah, you can do any kind of optimization that you would like to do. And this inner loop here then does not return the performance estimate, it returns a model. And you can use this model here to calculate the error on the 10% that has not been provided to this inner loop. And obviously you have to do it several times. As you know, you have to do repeated cross-validation in order to get reliable performance estimates. So, and this then would allow you to calculate a performance estimate that is fair, that is not over-optimistic, that doesn't include this kind of bias. But obviously, this is super expensive. Yeah? If you do the outer loop 50 times, repeated cross-validation, then you have to do cross-validation 10 times, for 10 folds, and then whatever your inner loop does. And when your inner loop also does cross-validation, or repeated cross-validation, which it should be, then you tend to end up with maybe millions of model builds. And this is why doing cross-validation right and doing machine learning right is really very compute intensive. But this approach, doing nested cross-validation, will provide you unbiased and robust performance estimates. Lastly, we need to talk about model stability. So model stability means that what you validate here in this procedure, it's not only the model, so the tree model or the linear model or the deep learning model you would like to use, but it's the whole procedure that is within your inner cross-validation run, where you also do parameter optimization, variable selection, and so on. And what you would like to see is that the models that are computed in this inner loop, it obviously depends on the data you provide with the inner loop. If you give it different data, then you would obtain a slightly different model. But the models you obtain should not be that different from each other. It should not be that on the one run, you get a model with 3 parameters. On the next run, we get a model with 20 parameters. So they should be all very similar in performance, but also in structure. Why is that? Well, at the end of this whole run, what you would do is to call this inner loop on your whole data set in order to obtain your final model. And therefore, you would like to have kind of stability here. Because if, like, whenever you call the inner loop, you get something completely different, something very small, something very big, sometimes something very good, sometimes something not so good, then how do you know what your final call of the inner loop will provide you when you provide the whole data set? And therefore, it's kind of important to check for model stability. And model stability means that the predictions you get from your different models are stable. And the models you obtain have similar hyperparameters. So going back to this slide, we call the inner loop to get the best model and then use this model in order to predict the left out data within the cross-validation. As we do this m times, let's say we do this 50 times, for each data point in our data set, we get now 50 predictions because each data point is present in one of these test folds. So we could check if these 50 predictions differ greatly. Yeah, they should be, let's say, 49 times should be the same value. That would be ideal. Yeah, it should definitely not vary that much. This is one thing to check for the predictions. And the other thing is check for the hyperparameters. These models you obtain here should have similar hyperparameters. It shouldn't be that you get a model with 3 parameters and the other one with 20 parameters. That shouldn't be the case. And if you have model stability, this means that you can actually be pretty sure that the model you obtain by your final call, so the final call is what you do at the end. Yeah, you call the inner loop on the full data set. If we find that we get similar models here with similar performance every time we call this, then we can actually be sure that the final call of the inner loop would provide us a similar model, yeah, with similar hyperparameters and similar performance. Therefore, you should also check for model stability. And with this, I would like to conclude today's lecture. As a quick summary, cross-validation is an amazing tool. It can help you to answer a lot of questions you have regarding your data. And it makes, the key advantage is that it makes much better use of your data compared to a traditional train test split. And even if you have tons of data, then CV can, even though you don't really need it, it can still be very useful. For instance, you could use it to check for model stability, because like whatever you do in statistics, if like the outcomes of your analysis change dramatically with minor changes of your input data set, then your results might not be very reliable. And therefore, cross-validation gives you these standard errors, and it can be very useful to look at that data. Cross-validation is indeed the gold standard for model assessment, which means assessing the performance of the model to know or to estimate how good your model will perform on unseen data. And for model selection, which means basically fitting the model complexity or like selecting the type of model that you would like to use with your dataset. Then two important concepts are repeated cross-validation, so do it several times in order to get more robust performance estimates and hyperparameter estimations. And lastly, you should also do nested cross-validation in order to separate the model selection and the model assessment, such that your performance estimates are unbiased. And with that, I would like to thank you and see you next time for the practical exercises.